Welcome back to Lecture 11 and GRA 6036. We have been talking about how to simulate data, and now I'll say something about the script that will soon be out on It's Learning and that you can read about in the lecture notes for today's lecture. So we are now at the point that we fit regression models to actual data. We do diagnostics, we look at the residuals, we evaluate if things are outlying data and so on, and to understand the tools that we are using and the assumptions we are making, it is nice to simulate regression data and look at what happens when we fit a perfect model and when we fit models that are not perfect. So what I mean by a perfect model is that, for example, if we say that this is a model for how x and y are related, then this is in reality how x and y are related. So I mean, so our model for the world is true. I mean, so yeah. So there is not some other function that is connecting x and y. It is a function of this form, and the only thing that are unknown to us is the value of this coefficient and this coefficient. And those, based on data, we can estimate these from data. So, okay. So let's go to this R script. So here we are simulating sort of what I here call perfect regression data. So first we set the sample size to 100. So that means that we have 100 individuals, countries, or firms, or units in general. And what we want to simulate is y's that are equal to beta 0, beta 1 times x plus some noise. And to do this, we have to set these values. So first I start out by making a covariate or independent variable, the x. Here I just draw x's with the same probability on the interval from -1 to 1. I mean, you could do this in other ways, because these x's don't really have to be random. You could fix them. So you could, for example, say if you want numbers between -1 and 1, you could do this, and that would give you numbers that are evenly spread on this interval. So if you look at these x's, you get we just drew some random numbers between -1 and 1. If we instead make our x like this, we get numbers that are evenly spread from -1 to 1. I mean, you can do whatever you like here. The important point is that the x value, the values of the covariates have to differ for each individual. I mean, if you just said, okay, I want everybody to have value 1, for example, or let's say 0 or 1/2, this would not work, because now there is no variance among your covariates. So you need some variance. So that is the only one for us now important thing. So you might do this, but I'll stick to the uniforms here. So now we have these x's, but we also need some values for beta 1 and beta 0. And of course, in reality, when we get regression data, x1, y1, x100, y100, these parameters are unknown to us, and we want to estimate these parameters from the data. But when we simulate data, we need to set these values. So now we just make some number. We just come up with some numbers here, and so now we can now we have x, now we have beta 1, and now we have beta 0, and then we need to say then we need to add the noise. And remember, the noise, what I here call eps, so these are the epsilons here. we assume that, well, those are all the other things that might influence y, but some things influence y in a positive direction, something influence y in a negative direction, and on average, their influence on y is 0. So that's why we are here drawing random normals with mean 0. And we need one such draw for each individual, so that's why we have the n here. And then we say, okay, how much variance do we want these to have? Well, here we say standard deviation 1, so variance 1. And now we simulate, so now we get the randomness, so to speak, and then we can simulate our y's. So then you can have a look, now we can have a look at these regression data. So we plot x against y, and we get this plot here. And since we are in the situation where we know the true regression line, so because we know beta 1 and beta 0 and beta 1, we can overlay the true regression line. So here it is. And notice that, so in this data, so this is beta 0 plus beta 1 times x, the blue line. And we see that with this regression data, the dots are evenly spread around this line. So it seems like the variance of the x's does not change. It's not dependent on where on the x-axis we are. And that, of course, is true because we simulated our data to have variance 1 that does not depend on the value of x. So the variance of these epsilons are the same no matter the value of x. And that is an assumption we are, so when that is here, the data is simulated, the data are simulated like this. But when we say, okay, we have, let's say we just have the xy data, we get this data set here, and we want to fit this model to this data set, then that is an assumption that we are making. So in this note, I talk about these assumptions. And this is, well, this assumption of the variance being the same no matter the value of the x's is important for the p-values and then also for the hypothesis testing and so on. So, I mean, the tests based on which we draw our conclusions. So if this assumption is not true, then our conclusions will be wrong. Okay, so let's now, we suppose that we only know y and x, and we are now to estimate the unknown parameters. Well, they're not unknown to us because we made them here, but now we act like they are unknown, so we fit this model. And the reason for calling this fit perf or fit perfect is because now we're fitting this model to the xy, the regression data. And since we simulated these data, we know that this is the perfect model. It's the correct model. So we can then go back to our plot. So we plotted, this is the true line, and now we can also plot the estimated line. So in reality, when we have real data, we would not know this blue line, but we would be able to estimate this green line. So we see that, well, the green line is close to the blue line, but it's not, they're not the same, because this is an estimate of this blue line, and if we have new data, we'll get a different green line. So let's see that. So the green line will change for each simulation. So let's so here, new data, the same blue line, but a different green line. One more time. The green line changed again. So we can then have a look at the summary of the fit. So here we see that these are our estimates. This is our estimate of beta 0, and this is our estimate of beta 1. And we see that, well, these numbers are close to the true numbers, but they are not the same, because these are estimates, while this is the truth. And I stress this, that when we have data, we do not know these numbers. It is these numbers that we want to say something about based on the data. Okay, so let's say something about residuals. I mean, to assess, one tool that we use to assess whether or not our model for data is a good model is by looking at plots of the residuals. And here we fitted what we know is the perfect model. So let's look at what the residuals should look like, or looks like, in a case that is perfect. So then we make our y hat, which is then fit perf qf 1 plus fit perf qf 2 times x, and then we take y minus y hat, and now we can plot. So these are the residuals. Now we can plot the residuals. Here, and there are some things to notice. So these are what the residuals are supposed to look like if your model is good, and here our model is perfect. So then they might look like this. So notice, so if we add a line on at 0, color red, well, we see that first of all there is no clear pattern in this in this plot. I mean, there are just dots spread around, and we also see, this is important, that the spread of these dots around 0, the red line here, is the same no matter where we find ourselves on the x-axis. So and that is, the reason for this is because here we simulated data where this noise does not depend on x. So it's okay, but when we fit this model, that is, or when we fit, not when we fit this model, but later on when we look at these p-values and make conclusions, or make conclusions based on these p-values, we are assuming that the noise is like this, that it does not depend, that its variance does not depend on x. And if the variance do depend on x, then our conclusions will not be valid. But by looking at this plot, so remember this plot we made without knowing anything about, we didn't use anything from our, we didn't use the fact that we know the truth here in this plot. And by looking at this plot, we could probably conclude, well, that the model is good. And here we know that it is a perfect model. So now we have something to compare with. So when you make residual plot of the residuals to real data, and you are wondering, is this a good plot or a bad plot? Well, then simulate some data and compare it to a good plot. So compare to this. Okay, so I'll make one more video.